Now I'm gonna just quickly talk about the homework. Now the most important part, when I was walking around, most people actually did. Most people got this part first page right, and the last part, last page here, most people did, as I assigned, only 1 to 4. Most of you guys did this without too much of a problem. I just want to remind you guys, make sure you show work at these kind of questions because it is very easy to have minor mistakes. Now, just to go over this section a little bit more, and I'm trying to drag this away somewhere, and I'm going to zoom this. Where's my flex? Yes. So I'm going to zoom in a little bit. Now, if you actually do this page right, you should be able to figure out, or helps you to figure out, the structure of the molecules later on. Okay. Now, but I'm going to just quickly do a few of these. So first one here, the example one, you see each carbon have a line that's pointed or connected to it. Yeah, Miss, what's our athletic director's name?
Miss Clark.
Yeah, she came and picked up all your stuff. Her office, maybe. Try the lost and found too. I'm joking. This is recorded. So anyways. So the carbon have 4 lines connected to it, which means each carbon makes 4 bonds. The hydrogen have 1 line connected to it, so it makes 1 bond. Okay? And I'm going to do this one. Again, the carbon have 4 lines to it, so each carbon makes 4 bonds. F is fluorine. Fluorine have 1 line to it, means each fluorine makes 1 bond. Okay? And if you look at this one again, fluorine, each one have only 1 line connected to it, so each fluorine makes 1 bond. So if you do the rest of these properly, you should figure out the pattern, right? You should figure out a pattern like, for example, carbon here. Oh, carbon, you should know this, hey, they usually form 4 bonds, and in terms of the periodic table group, I think this class is pretty good. But if you look at your periodic table, your group numbers are up here. So the Roman numerals, these are the group number. 1, 2, 3, 4, 5, 6, 7, 0. So in this case, carbon is at group 4 here. So you will write that carbon is in group 4. Okay? And fluorine, it tends to make only 1 bond. And fluorine, it is at group 7. So in this case, you say group 7. And then you fill in the rest. And then later on, you notice even more pattern and generalization. You can realize that, hey, everything in group 4 tends to make 4 bonds. Everything in group 7 tends to make 1 bond. Stuff like that. Okay? Then you are able to have a generalization of this. And from that point on, you should be able to figure out structures. So for example, if I'm giving you something like, let's just say if I give you a formula, C2H2. Okay? C2H2. So you know there's 2 carbons. You know that there's 2 hydrogens. You know hydrogen only form 1 bond. So you do this. It can't be just like this. And it's like, oh, it's not going to work. So hydrogen form 1 bond with the carbon, and now you know it's like, oh, each carbon needs to have 4 bonds. So since it formed 1 with the hydrogen already, so it must form like this. Do you guys follow so far? So by knowing how to do this properly, you should be able to deduce and figure out most of these molecular structures. Questions? No? Okay. Now, as I said before, the second part, the top part here, 1 to 4, make sure you just do the work. Show your work carefully. It seems like you guys are doing well already, okay? Because it's very susceptible to minor mistakes. Any questions? Yes, no, maybe, no? Now, what we're going to do today is this. We're going to be talking about a topic called activation energy, something called activation energy, and heat of neutralization. Activation energy and heat of neutralization. Now, this is kind of going to be built on what we learned about yesterday. So, now just a quick review. So now, both kind of chemical reactions, you always, so time, energy level. So both of these kinds, you always start off with a reactant. Now the reactants always have some sort of energy level. Now this energy is stored within the bonds of the molecule. So the single bond, the double bonds all have some bond energies. So that's what you're talking about. So at a chemical reaction, there's always for it to start, you always need to put in some energy to break all those bonds. So there's this endothermic process or endothermic part of the chemical reaction. So where it breaks all the bonds of the reactants, so you reach a state where there's no bonds between atoms. Okay? No bonds, or these, it's a mixture, really. So it needs to break all these bonds. You need some energy to it, and because it's a chemical reaction, you will form new products. So let's just say if the product is down here, at this energy level, for it to form new products, it has to form new bonds. And as we said yesterday, forming bonds releases energy, gives off energy. So this is the part where it's an exothermic part. And because in this particular example, it is more exo than endo, so in this case, it gives off more energy than the energy you need to put in. So in this case, overall or net, this is an exothermic reaction. This is an exothermic reaction. We talked about this yesterday. Whereas on the other side, if you have, let's just say you start off pretty low, your reactants have pretty low energy levels, you have to put in a lot of energy to break up all these bonds. So you have a lot endothermic part. To break up all these bonds, atoms, and then when it forms new bonds to make products, it only releases a little bit of energy. So if you have a situation like this, where you put in more energy, there's more endo than exo, the amount of energy give out when you forms new bond. So in this case, you would have an overall endothermic reaction. It's more overall endo. Good so far? Now, we also talked about another thing. We also talked about heat of reaction. Remember, heat of reaction is how much energy that it's either given out or absorbed by the overall reaction. And you can look at this from really, you're comparing the energy level between the reactants and products. So in this case, in the exothermic reaction, because you start off here as a reactant energy level, and end up you're going to give off, you're going to drop down here to the products, you're really giving off this much heat. So your heat of reaction is here. You go from here to there, and it is always negative. Do you guys follow so far? Whereas for the endothermic reaction, your reactant have low energy level, your product have pretty high energy level. So in this case, you heat a reaction, the amount of energy that is absorbed is positive. It takes in more energy. Do you guys follow? So all this is from yesterday's notes. Now today what we're going to be talking about activation energy, it is not exactly new. It is going to be a little bit of a review. It kind of built on what you learned from yesterday. Okay. Now, here, this is this beaker that I used a demo yesterday, and you can tell there's still a little bit of alcohol left. Okay, there's still a little bit of the ethanol left. Now, if you think about it, this ethanol has been sitting overnight in this bench, interacting with the oxygen overnight. Nothing happened to it. It didn't start off a fire. Why is that again? Why didn't it go on fire overnight? What do you mean by no activation energy?
No product that causes it.
No, not because there's no product. You could have a product if a reaction started, but why this reaction didn't start? The ethanol is still there, the oxygen is still there, but there's no reaction. Why is there no reaction? What did I need to do to have the reaction?
Small amount of energy is needed.
Small amount of energy. Remember, small amount of energy is needed. Like yesterday, I throw in a match, a lit match in there to get the fire started. I have to put in a little bit of energy to break all the bonds of the ethanol and the oxygen to get to this state. Okay? So you do need a little bit of energy to get the reaction going, whether it's exothermic or especially endothermic. Do you guys follow so far? So you do need to put in some energy. Now, this energy, we actually have a name. Just like what they would guess, it is called activation energy. Now this part here, so we're not going to call it endo anymore. We can easily cross that out. It's not endo. You don't call that endo anymore. We actually call it activation energy. Now, because we don't have that much space here, there is actually a short form for activation energy. Activation energy has a short form. It is known as, anyone want to guess or no? No one want to guess? ACT? What? David, what were you saying? No? No one want to guess? AE? No, it's not American Eagle. But okay. What is the company that made the video game FIFA?
EA.
EA. All the boys. Yes, it is actually EA.
Ooh,
okay?
Easy to memorize.
Because it is energy. It is a form of energy, and it's what form of energy? Activation energy. EA. Okay? So this here, EA, so this for energy level that requires to break all these bonds, that's activation energy. Okay? So that's activation energy. Energy to break all the bonds between the break all the bonds in all the reactants. That's EA, activation energy. And you do have a textbook definition that you should write down. So, if you can, do you guys have this down already?
Yep.
Okay. Okay. Please copy this section down. Zoom in.